on the topology of Rn. So Rn, you know what Rn is. Rn has a structure called a topology. So a topology is a structure that you put on a set in order to give it some sort of properties. And the properties that we're looking for is called locality. So locality means that if you have x, if you have some point x in Rn, you can draw neighborhoods around x. So if you have like R2 and you pick a point, you can draw points, or you can draw neighborhoods around this point and neighborhoods within neighborhoods, and there's sort of some distance defined to the boundary of the neighborhood, and you can check whether neighborhoods are connected or not, whether they have some kind of bridge connecting them or whether they're disconnected, and so on. So this is important, and this is sort of what we're looking for here. You've heard of topology in sort of some other contexts like coffee mugs and donuts. This is sort of a more general topology type of picture. There are other forms of topology. There's algebraic topology, and we'll talk about that later in the course, but for now what we're going to do is we're just going to look at sort of the study of neighborhoods. So what does it mean for a set to be open or closed or compact when it's sort of a neighborhood around some point? So, all right, let's begin with that. So let's say that we have to define what open means. Open sets. A set is open if, well, it doesn't contain its boundary, for one. That's what you've learned in school so far. So A comma B. This interval is open because it doesn't contain A or B. But there's sort of a more general definition of open, and we'll see how it connects to this one. They're equivalent, but there's a more general one that also works. So I'm going to consider, to just give you a nice visual picture, some blob around a point x. And this blob has got to have the property that for any other point, I'll call this y, you can always draw some neighborhood around y, which is a ball, which I'll call B. So B is some neighborhood around y. It's z such that the distance between y and y minus z is less than epsilon. Right. So yeah, if you have this point y, you can always pick some ball which has some distance away from y such that y is contained within b and b is contained completely within this outside region u. So, okay, what we mean by open now. Open definition. A subset U of Rn is open if for all y in U there exists epsilon greater than 0 such that the ball of radius epsilon centered upon y is a complete proper subset of U. So this is what it means to be open. And similarly for closed, a subset U of Rn is closed if the complement of U is open. Great. So now let's see how this connects to our sort of intuitive definition of open in terms of intervals. So let's zoom out a little bit. Let's say we have some open neighborhood U. And I want to look at sequences in U. I want to look at sort of what happens when we approach the boundary. So let xn be a convergent sequence in U. So that is xn is an element of U for all n. So let I'll call it LU be the set of sequences in U which converge. Okay. Then the set of limits is called the closure of U, and it's written close of U equals U bar. So this is sort of what we mean by the boundary. If we have a limit xn, it's going to converge either somewhere in U, so this could be the limit, or we could have another sequence yn which goes all the way up to the boundary, and that's where its limit is. In this case, y doesn't have to be contained within U. We just require that each yn is contained within U. So points in U bar minus U are called boundary points. So this is sort of, if you took the entire set including the boundary and you got rid of the stuff in the center. So U bar minus U is defined to be the boundary of U, and I'll denote it with this backwards B. It looks sort of like the Basics logo, if you've ever seen that shoe brand before at Walmart or something. So this is the boundary of U, and the reason why we call it that also, there's another definition of it. So we could say the boundary of U is the set of x in U, or the set of all x in U bar, such that x has some epsilon such that, or for all epsilon actually, not just some epsilon. So for all epsilon greater than 0, the ball with radius epsilon around x intersects both U and the ball of radius epsilon around x intersects U closure or complement. In fact, this could be extended to all of Rn. So here's the idea. If you have some point on the boundary, you can always draw some circle around it, and the circle is going to intersect the outside and the inside. So this is the inside and this is the outside. So these points are called boundary points. These points are called the interior points. And the whole thing is called the closure. So U bar is the interior of U unioned with the boundary of U. Great. So that sort of covers the basic definitions of a topology just for Rn. Of course, there's sort of more complicated notions of a boundary and more complicated topological spaces. So note that this stuff needs more explanation in a general topological space. And that's because the notion of a sequence isn't always the same. In fact, some spaces don't have really a notion of convergence of sequences. They have convergence of nets, and it's quite a lot different. So we'll see that a little bit, but I think we're just going to stick with this sort of metric space style topology. So let's look at general metric spaces. So moving away from Rn. Let's sort of see how that goes. So a metric space is a space m comma tau. So it's a space, it's a set with some topology. I defined that, right? Oh, no, I didn't. So, right. A metric space is a space M, and tau being the set of all open sets in M. And we have the requirement that it has to have a function which goes from the space to R, and it needs the property that, well, first of all, d of x and y needs to be greater than 0, so the distance can't ever be 0. But not only that, the distance is only 0 if and only if both the points are the same, or yeah, that's it. They can only be 0 if the points are the same. That makes sense, right? So finally, it has to have the triangle inequality property as well. So d of x comma z. So we can view this in this way. If you've got 3 points x, y, and z, the distance between x and z has got to be less than or equal to the distance between x and y plus the distance between y and z. So this is called the triangle inequality. So we saw this before in Rn. If you've taken any sort of course covering metric spaces, and now we're sort of extending it to general spaces. So this is the idea, and you can always sort of construct a topology from a metric. So what I mean by that is if m comma d is a set with metric d, then we can find a collection of open sets tau such that tau is generated by balls with respect to this topology. So that means that any sort of open set is defined to be some set which always contains open balls. So that is for all u, which is an open set, if x is in u, then there exists epsilon greater than 0 such that b epsilon with respect to the metric D of X intersects U, in fact, is completely contained within U, right? So this open set B epsilon D of X is just defined the same way as an open ball. So you pick all Y such that the distance between X and Y is less than epsilon. Great. So this sort of defines a general metric space, and this is how we sort of get all the open sets in the metric space. So the topology of this space is completely determined by D. In general, though, you pick tau before you pick D. So what we did at the start of this lecture was we picked D. We picked D to be the absolute value of X minus Y. But in general, what you're going to do is pick the sets first, and then you're going to see if you can find some metric. So this is an interesting way of doing topology. So formal topology. A topology on M is a set of subsets of M such that 1, if U and V are in the topology, then the union of U and V is in the topology. In fact, all infinite unions over open sets is an element of the topology. Second of all, if U and V are elements of the topology again, then U intersect V is an element of the topology. But this only holds for finite indexes. So I have to pick some finite subset of the integers to index over in order for this to be a valid topology. Otherwise, well, it's stronger than a topology. And third of all, the whole set is open. So M is an element of the topology. This kind of makes sense. The intuition behind this is that, well, if Rn is a topological space, then Rn itself is open. Because, of course, every point x in Rn has the property that x has an open ball which is contained in Rn. That's obvious. And finally, the empty set has got to be in the topology as well. And that's because there aren't any points in the empty set, which means that they all have the property that there's some open ball with the open ball contained in the empty set, because there are no open balls in the first place to worry about. So this is sort of like a vacuous definition. So this doesn't really matter, but it's included just to be absolutely clear, and because there are really weird edge cases that you can find in some books. So for example, there's a book called Counterexamples in Topology. And there you can see a lot of crazy examples where you start with a set M and you add some topology tau, and then you maybe add some metric D. What we did was we moved from D to tau. So this is workable for Rn, but in general, you start with the open sets and then you construct a metric. So there are some sets have no metrics. So these sets are called non-metrizable topological spaces. So start with a set M and a topology tau, can you construct a metric? So sets that you can construct a metric are called metrizable. So it only works if it's metrizable. Great. So that's sort of the idea behind topology. And I think now I guess we can talk about sequences a little bit. Have I talked about sequences very much? Let's see. Talked about, right, the limit points and the closure. So let's look at that in a little bit more detail. Yes, so I guess we can talk a little bit now about completeness. So if I'm going to show you that sort of completeness is an important concept and why it's important. So Rn has the following property. This sort of motivates completeness. So Rn has the property that if Xn is a sequence such that Xn minus Xm goes to 0 as as n and m go to infinity, it's called Cauchy. And so if Xn is a Cauchy sequence, then Xn converges. So what does this mean? I can draw you a picture of this. If you have a sequence of points in Rn or whatever, then it's only going to converge if and only if the points in the sequence get closer and closer to one another. So that's kind of obvious, right? They have to approach some kind of asymptote, so they have to get closer and closer together. But you know, some spaces have the property that not all Cauchy sequences converge. And in fact, not all sequences have a convergent subsequence. So this is important, actually. If we have, for example, Qn, and we have a sequence in Qn, for example, Xn equals the digits of pi. So the floor function of 10 to the n times pi over 10 to the n. So this is 3, 3.14, 3.141, ... So this sequence, well, it doesn't converge to an element of Qn, it converges to an element of Rn minus Qn. So Xn converges to pi, but Xn, hold on, this doesn't really work, does it? Yeah, it does, okay. So Xn goes to some limit x, which is not an element of Q. So this is not great, because we want, if the sequence like converges, then it's gotta like look at this. You could just cancel the 10 to the n outright, and it'll basically obviously converge. Yeah, okay, so that's a nice little example there of why Q is not complete, but R is. So R, if Xn minus Xm goes to 0, then Xn goes to some limit x. That looked like an infinity, not an x. Great, so in fact, because Q is a subset of R, and well, it's dense, we call Q or R is the completion of Q, or a completion of Q. Of course, this relies on the metric that we're using, because there's, of course, an absolute value here. So this is d of xn xm in general. Yeah, so if we chose a different metric for Q, we could get a different completion. So let's say we have the rational numbers, and we want the rational numbers to sort of be filled in. You want all the sequences to have a well-defined limit. Well, you can get R if you use d of x and y equals the absolute value of x minus y. But you can get other numbers. So you can call this one QP, which is called the P at x. And these are a completion of Q, but we're not going to go this route because, well, it's just not relevant in differential geometry unless you're doing p-adic differential geometry, which is probably a bad idea. But, you know, I don't know. Okay, so anyways, I went on a little bit of a tangent there. Another great property of topology is the notion of compactness. So this really deserves its own video on its own, but I'm going to do it now anyways. Compactness is sort of, well, in Rn actually. I'm only going to touch on it in Rn just for now. But a compact set in Rn is one which has the property that, okay, so U is the set, U has got to be closed and bounded. So that is, there exists some D in R such that the ball of radius d centered at 0 contains U. So that's what we mean by bounded. It's got some finite diameter d. And you know, this has some nice properties. And the main property that it has is that if xn is a sequence in U, and xn is Cauchy, then xn goes to some limit x contained in U. So essentially these are the sort of complete subspaces of R. Now, not only that, but if xn is a sequence in U, then xn has a convergent subsequence, and I'll call it xnk, such that so that xnk goes to some limit x in U. So this is pretty awesome. This one is just sort of a definition. Compacta are complete. And this one is more important. This one's called the Bolzano Weierstrass theorem. And I can give you a proof, or a sketch of a proof. So the idea goes like this. If xn is going to have some spikes. So you figure out a way to define these spikes, and they're going to be something like hn equals Right, so the nth point x k such that for all n or for all k greater than n, xk is less than xn, something like this. So basically you pick this one to be the first spike because it has the property that anything past it is less, and you pick this one to be the second spike, and so on. And of course, if there is no spike, well, that means that for all k greater than n, there must be that xn must be greater than xk, and that means that there's a peak. So what you could do is, instead of looking at descending chains of points, you look at ascending chains of points. Either way, one of these things is going to be a monotone subsequence of xn. And the monotonicity gives us the convergence, because what you have is x and k is monotone, and x and k is an element of some closed set, and therefore x and k converges. So x and k is a monotone converging subsequence by the monotone convergence theorem. Right, so I think that covers everything I can do in one lecture. Yeah, and I'll see you next time.